So, one of the themes of this program is geometric problems that come from physics, and a very classical one is moduli space monopoles. And Nick has very kindly agreed to give a talk about physics and moduli space dynamics and solitons.
Well, thanks for giving me 90 minutes to talk about this. So this is the first talk about here about the soliton kind of moduli spaces, and there are various examples of them. We will hear about various types of soliton, and I thought I'd concentrate on vortices and monopoles, which have some overlap, but you'll see that there is not too much similarity between the parts of my talk. So since I've got 90 minutes, I've prepared about 45 minutes on vortices. I hope I don't overrun too much. And then about 45 minutes on monopoles. I may make a short break between those. So I will describe a little bit the background, the actual equations that one gets, and then how one gets a moduli space, and how one defines a metric on it. Then the basic idea is that geodesics on the moduli space of these solitons represents the motion of these solitons relative to each other at relatively slow speeds, which in practice means just non-relativistic speeds. So this is a non-relativistic approximation to what actually starts as a relativistic field theory. But I won't make much of the relativistic aspect. But in particle physics, of course, we're interested in relativistic theories because that's what we know experimentally is right. So this is sort of the outline. There are sort of various sections on vortices. I'll talk about just the abelian Higgs vortices. These are solitons in 2 dimensions, and they can be studied in the plane. But it turned out to be quite interesting to study vortices on curved surfaces. So the effect of the background curvature on a vortex is interesting, and it affects even one vortex. So I will talk to some extent about one vortex on a curved surface and how it moves. I'll say something about n-vortex moduli space geometry, and that will actually be in a general curved background, although, again, it could be just flat plane. Using this n-vortex moduli space geometry, one thing I can do is work out a physical thing, the statistical mechanics of vortices. So this is some kind of limit. It's some sort of asymptotic property when you've got lots of vortices on a big surface with a finite density. And I was interested in their statistical mechanics, which in principle, which is at finite temperature. What is the pressure? Do they behave as an ideal gas or as a non-ideal gas? And we have an answer to that. Then another technically interesting thing is, this is for a general curved surface, but it's rather interesting to look at the asymptotics. It's typical of physicists that they're interested in asymptotic behavior, various limits. And one limit here is if the surface has small curvature. So it's a big surface, the vortex has a finite size. How's it affected by the curvature? What is the asymptotics of that for small curvature? And then that's the end of the section on vortices. Quite a lot more is known about vortices, but I'm limited time. And then I'll talk about monopoles in the second half. So these are these Bogomolny-Prasad Sommerfeld monopoles. They are related to Yang-Mills instantons, but down in 3 dimensions rather than 4 dimensions. And here I will be working in flat R3. It would be actually quite interesting to study monopoles on a curved 3-dimensional space. One could try and do something similar to this. This section 4, apply it to one monopole. How does one monopole move on a curved R3? But that hasn't been looked at as far as I know. And then something one can do for monopoles, which is interesting, is to study the geodesics and the moduli space metric when the monopoles are well separated. I mean, it's worth doing this because it's difficult to study monopoles when they're close together. And things simplify when they're separated. Then they behave like point-like particles, and one can have a physical insight into how the monopoles interact, and that gives insight into the moduli space metric. I mean, one can rederive the moduli space metric for well-separated monopoles, and some conclusions. So that's, again, another sort of asymptotics, well-separated monopoles. So the separation is a large parameter. So let me set up these vortex equations. An abelian Higgs vortex is a topological soliton on the surface. M a vortex has a definite size, unlike instantons, which have a variable size. So vortices have a definite size. There's a length scaling problem. They have a quantized magnetic flux. This is the physicist's way of saying that they have a definite first Chern number. The surface, I'm going to need some coordinates. So real coordinates x1 and x2 we combine into a complex coordinate z. So it's a Riemann surface with this metric, which is conformal to the flat metric. So the metric is determined by a single function of where you are on the surface, and this is in real language. I think I'll usually use this language. And then, if the surface is curved, it has an interesting effect even on one vortex. Now, there's a gauge theory and a Abelian gauge theory, so there is a Maxwell vector potential. So the gauge group is U1. There's a complex scalar field interacting with the Maxwell vector potential. A complex field produces electric currents, and the vortex has a current loop going around it, and that generates a magnetic field. So it's a gauge theory in that sense, but an Abelian Maxwell type theory. These are the spatial components of the vector potential, but you see I'm going to study moving objects, so we will be working in 2+1 dimensions. The metric will be trivial in the time direction, so even though the space is curved, the time will just add to the metric with a dt squared. And there'll be no cross terms. So that's an assumption. You don't have to make it. And if you have time-dependent fields, you must include a time component to the gauge potential. This is sometimes called A0, but I'll usually write AT. These vortices are moving on a curved surface, but I'm assuming that there's no gravity in this theory. There's no Einstein equation. The vortices have no back reaction on the metric. In other words, this function is completely arbitrary. It's not constrained in any way by either Einstein equations or the presence of the vortex. It will be interesting actually to include that effect. There's some work on gravitating vortices, but to actually study moving gravitating vortices is quite tricky. And that's beyond this talk. So one starts with an idea of an energy function for static fields. There's some coupling constants in this theory which I've normalized, but the important thing is I'm working at what's called critical coupling. That's where this term in the energy has coefficient 1. Generally, this could be not equal to 1, but critical coupling means it's 1. That will lead to the Bogomolny equations. That's the condition that leads to the fact that vortices have no static interactions. They only interact when they're moving. So this is a standard kind of physics. So energy function, there's a magnetic field, F. So F is the usual for field tensor in 2 dimensions. And then it comes with a 1 over omega squared because of the background geometry. There's the covariant derivative of this charged scalar field, which couples to the gauge potential. And there's also a factor there, but this actually cancels. So this term doesn't depend on omega. And then there's what's called this Higgs potential. You see its minimum occurs at mod phi equals 1. So the vacuum is mod phi equals 1. And asymptotically, a vortex has the boundary condition that mod phi goes to 1. So phi will be 0 at the center of the vortex, but asymptotically phi will be definitely non-zero. Then we have this Chern number condition that the integral of the field tensor over the surface is 2 pi times integer. This is, and I'm going to assume n is positive, so I'll be talking about vortices, not anti-vortices. And so I assume n is a positive. So n is an integer, that's a theorem. It's the first Chern number of the field over the surface. And I'm going to assume n is positive, so we're talking about vortices rather than anti-vortices. And then heuristically, the vortices have centers. That's where phi vanishes. And it will turn out that for the Bogomolny type vortices, phi vanishes at exactly n points counted with multiplicity. And so you can identify the vortex locations with where phi vanishes. By the way, that's what makes studying vortices different from monopoles. There's a field phi for monopoles, but you can't just look at the zeros of phi to say where the monopoles are. But for vortices, you really can in a strict way. And then it turns out also the magnetic field is concentrated where the vortices are, and so actually the magnetic field which physically is this 1 over omega times f, has a maximum where phi is 0, as we'll see from the Bogomolny equation. So one of the important tricks is this Bogomolny argument. You start with this combination, then you complete the square. You combine this term with this term and complete the square, and that's already square, but you slightly manipulate it. So V can be rewritten as this sort of sum of this F term and this Higgs potential term squared, and there's some cross term come out of this. In particular, the cross term 1 times F comes out of that, and when you integrate that up and sort of cancel it off, that gives this Chern number contribution. So this argument shows that V is this pi times the Chern number plus this. And this is the Z bar derivative of phi, which combines d1 of phi and d2 of phi. And so this is greater than or equal to 0, and so there's a lower bound on V, which is pi n. And Bogomolny vortices exactly saturate this, so V is pi n, and that requires that this is 0 and that's 0, and those are the Bogomolny equations which vortices satisfy. So the minimum energy fields for given n satisfy these Bogomolny equations. dz bar phi is 0, which says that phi is holomorphic in some sense, and the field strength is directly related to the scalar field mod squared. And here you see that this is maximal where phi 0.
Was there a cross term between f and phi squared in your original?
Yes, that cancels against a cross term here. This combines d1 of phi with I d2 of phi, and there's a cross term there, and you have to integrate by parts. You get a commutator of d1 and d2, which cancels against the one you mentioned, and there's a total derivative term left, which integrates to 0 on a compact manifold. It's strictly in exact form, the cross term, so it integrates to 0. Yes, so indeed, I've skipped 1 or 2 lines in this derivation. A nice result for a compact surface is that the number of vortices is not arbitrary, it's constrained by the area. You see that by integrating this equation. If you integrate this integral of this gives n, basically, and the integral of 1 gives the area when you integrate over the surface. And because this is negative, this term, n has to be less than something times the area, and 4 pi. So 4 pi n is less than the area. This is the area, just the integral of omega d2x. So for a given area, n is bounded in this way. And the physical interpretation is that so each vortex occupies an area 4 pi, and so on a certain area, there's only space for a certain number of vortices, because every time you put one in, it sort of has an area 4 pi. It's not, they're not hard disks. They can overlap, but they sort of occupy an area 4 pi. You can put more vortices on, but not solve the Bogomolny equation. So if you try and force more than this bound onto the surface, that's perfectly okay, but you raise the energy above the Bogomolny lower bound. So there's some sort of repulsion between them.
Yeah, sorry, just to be clear, so your manifold it's a compact
Oh,
manifold
sorry, yes,
without
it is.
boundary.
Yeah, that's right. So there's on 2 cases. Either it's an open manifold, in which case this bound has no effect. So in a plane, you can have any number of vortices, but on a compact manifold, there's this bound. As I say, it's not an absolute bound on. You can force more vortices on, but they don't satisfy this Bogomolny equation. Then, if n is an allowed value, you can put the vortices where you like. This is basically Taub's theorem, originally in the plane, but generalized by Bradlow and Gauss-Prada. So you can choose n points freely on the surface. They can also coincide. And then the Bogomolny equations have a unique solution up to gauge transformations with the vortex centers at these n chosen points. And sometimes I'll be talking about one vortex, so I'll then call the center Z. So these points are where the Higgs field vanishes. And then, with those specified, there's a unique solution. And this tells you what the moduli space is, because it's the moduli space of n points, and they're unordered.
They have to be distinct.
I'm sorry?
Distinct points.
Well, they're unordered. No, they are indistinct. indistinguishable, you see, because we have
No,
vortices
can
at
two
2
of them be
points.
the same?
Yes.
Sorry?
Can two of
Oh
the
yes,
sectors
they
be the
can
same?
coincide. Yes, you can have, you know, a coincidence. Yes, they can coincide. Yes, yes. But they, as I say, they're indistinguishable. So the moduli space is the nth power of the surface. So moduli space, I use this calligraphic M, and the n vortex moduli space is the nth power but symmetrized. So this is the permutation group, and it's sort of well known result in complex analysis that the symmetrized nth power of a manifold is smooth. So you might think it's an orbifold. I mean, m to the n is obviously smooth, but if you quotient by this, you might think you get an orbifold, but you don't, because the effective good coordinates are the symmetric polynomials in these sets. So these are actually not good coordinates globally because of the permutation symmetry, but if you take the symmetric combinations, then they're good coordinates. Symmetric polynomials. So this moduli space is as a, before you consider a metric, as a complex manifold is smooth and of complex dimension n. So now one can go back and solve these Bogomolny, well, reduce the Bogomolny equations. So this is a solvable equation. This, if you expand out, this equation determines a z bar, the gauge potential, in terms of derivative of phi divided by phi. So in other words, the derivative of log phi. So you can solve that first equation to get a z bar is a derivative of log phi, and this is sort of a real gauge potential, so AZ is the complex conjugate of AZ bar. And then when you substitute, you can work out then the field tensor in terms of phi, and you get something like this, log of mod phi squared from these two terms, and you get a Laplacian because you need another derivative to get the field tensor, dz of this, which gives dz bar here. So you get the Laplacian of log mod phi squared, and then the terms that were there previously. So you get this 1 minus mod phi squared. This becomes a Laplacian of log mod phi squared. So this is the covariant Laplacian, 1 over omega dz bar. And then formally the equation gave 0 on the right-hand side. But in this formulation, because phi vanishes, log mod phi squared has logarithmic singularities, and when you take the Laplacian of that, you get delta function. So assuming that phi has these zeros at these points, capital Z, you get delta function sources for this phi field. And this formulation is called Taub's equation, so reducing the Bogomolny equations to just a scalar equation for mod phi. And actually, there's another version. If you put mod phi squared is e to the h, then you get an equation for h. And that's Taub's equation, which originally was in the plane, but is also valid on a curved surface, provided you throw in this omega. Right, so we've got these vortices. So, you know, Taub's Gaussian Price-on proved that this equation has solutions. And there's a unique solution for given sources. So now, what is the moduli space and what is its dynamics, metric? So there's a dynamical theory of vortices, and you start physically with a kinetic energy, which involves the electric field squared and the time derivative of the scalar field squared. So E is the time derivative of the gauge potential with this correction term involving AT, and dt phi is the time derivative of phi with, again, a correction term. So this is gauge invariant, and there's an equation I've written down, which is Gauss's law, which involves the divergence of E and some additional terms. Gauss's law determines A of t physically, and means that AT is not just arbitrary, but it means that E and dt phi, the projections of these first terms, orthogonal to gauge orbits. So this term subtracts off an infinitesimal gauge transformation, and so does this. So that's the effect of Gauss's law and what E and dt phi mean. So this is this gives us this means this kinetic energy gives a measure of, you know, how much energy there is in true motion of the gauge field and scalar field. You know, not just gauge transformations, but orthogonal to gauge transformations. When we go to the gauge AT equals 0, which gets rid of these terms, provided these terms are already orthogonal to gauge orbit. So you have to sort of do some gauge fixing, and then you are allowed to set AT equals 0, and then you get this kinetic energy. And this is sort of the physical version of what's just the norm in field space, which defines the L2 metric on field. So time derivatives just turn into sort of deltas, infinitesimal variations of the gauge field and the scalar field. So this is where mathematicians would, I think, start, but it corresponds physically to that. And then the metric on the moduli space is that sort of field theory metric restricted to the moduli space and with gauge degrees of freedom quotiented out. So that gives a metric on this, what is a manifold of complex dimension n. And then there's a sort of general physics argument which says that having found a metric on the moduli space, if you're interested in vortex motion, you just have to study geodesics on the moduli space. So this is based on a physical idea that the Bogomolny equations represent minima of the energy, and among the fields satisfying the Bogomolny equations, the static energy is the same, because it was just pi n. And so therefore it's like you're at the bottom of a bucket with there's a potential well, but you're at the bottom. And the bottom is some manifold, it's the moduli space. And the moduli space has no potential energy on it, but it does have metric structure, and hence it's sort of kinetic energy. And the motion is along geodesics because that is the natural motion of a dynamical system if there's no potential energy. Only the kinetic energy matters, and the motion is sort of free motion on the manifold, which is geodesic motion. So that's the physical argument that one's interested in geodesics. They describe the non-relativistic motion of n vortices on the curved background surface n. And these geodesics are highly non-trivial, so the vortices do scatter. Even though there are no static forces, there are these velocity-dependent forces implied by geodesic motion, and the vortices scatter. And even for one vortex, the metric on the moduli space differs from the underlying metric on the manifold. So the geodesics on the one vortex moduli space describe vortex motion, one vortex motion on M, whereas the geodesics on M itself, with the original metric, that would describe point particle motion. And these are not the same, so it's quite interesting to see what the difference is between how vortex moves and how point particle moves. The difference is small if the curvature is small. Right, so there's been a lot of sort of further progress in understanding this moduli space metric for vortices, and there's nothing analogous to this for monopoles that I'm aware of. So we start with a sort of defining integral for the metric on the moduli space. That's some integral over space, so this one. But one can do something with this using the Bogomolny equation. So first of all, you express the variation of the gauge field and the variation of the scalar field purely in terms of this eta, which is the variation of log of phi. I mean, these are related because of the fact that this is completely determined by that, if you remember, involving this derivative of the log. So, and then you can trade this phi for this gauge invariant thing, which is h. So each gauge is mod phi squared, that's gauge invariant. And one finds that this field metric, which down here can be sort of re-expressed in terms of purely this quantity eta, which is the variation purely of actually of h in disguise, and you get this expression still as an integral over the underlying manifold. But now this eta is a tangent vector to the moduli space, so it obeys the linearization of the Taubes equation. Because the phi, mod phi, h obeys the Taubes equation, so this eta obeys some linearization of that. And here's the linearization of the Taubes equation, actually combined with Gauss's law, is important physically. And you get this nice linear equation for the eta satisfies. And it's not strictly zero, there are also some delta functions, derivatives of delta functions at the sources. And the solution is explicit, it's sort of just a variation of h, because it's the linearization of the Taubes equation. So if you vary h with respect to the vortex locations and combine these variations of the vortex locations, you get a solution of this equation. And so we can substitute this expression into here. And then you can integrate by parts. You can shift, I mean actually this omega cancels, so you can shift the dz onto here and you get this Laplacian of eta, but that's given by this equation. So you can integrate by parts here and everything simplifies. But you pick up boundary contributions from around the singularity. The singularities are these positions z. And this is the localization formula for idea of Ian Strawn and Trevor Samuels. Strawn did it for hyperbolic vortices, and Samuels did it for more general, for flat space vortices and more general surfaces. So what happens is that for n vortices at these points, the metric reduces to just now a sum. There's no integral anymore. There's a sum over the double sum over the points. I've written out in infinitesimal language, and you get the background metric contributing, but you also get this term. And this is the contribution from near the singularity. So when you do this integration by parts over the surface, if here's one of the positions, you end up having to do a line integral around a small circle. And it turns out that picks up then this term here. And what is this B, which is sort of the key quantity here in this formula? Well, it's the coefficient in the expansion of mod phi squared around the vortex center. It's what contributes when you do a small line integral. This has radius epsilon, when epsilon is small. And so you have to do an expansion. Mod phi squared is a sort of leading term, which gives the logarithmic singularity. So if you take the log of this, you get log of this squared. And that's the leading term. It's got some coefficient, which is quite important. But then it's the subleading term, which has the b in it. So it's the, in this Taylor expansion, when you sort of remove this bit, it's the coefficient of the linear term that gives a non-zero result for this line integral.
When you did the integration by parts, do you know you're not picking up anything in infinity?
Yeah, I'm assuming, yeah. So on an open manifold, that it goes to zero. That, yeah, in the plane, yeah, there's no contribution from infinity.
If it's a plane.
If it's plane, well, yeah, if it looks asymptotically reasonably planar, I think that's not been looked at. If M, for example, has a cylindrical infinity, it's not been looked at what that contribution would be. Yeah. So, yeah, so, and on a compact surface, there is no infinity. But that's an interesting question, yeah, so for more general M's that I'm considering, what might be the contribution? So this looks complex, but a metric should be real. So purely because this metric is real, it's kind of obvious that this has to be true. And that was actually Samuel's original argument, that this must be true to make this real. But actually I proved it using some Green's function argument that this identity holds. Okay, so the B's are these linear coefficients, and what do they depend on? They depend on the background surface geometry and on the effect of other vortices. The B is a measure of the lack of circular symmetry of the field near the vortex. So roughly speaking, on this circle, the vortex field mod phi is circularly symmetric. And if you have one vortex alone in a plane, it's circularly symmetric and B is zero. But if this is curved, or if the other vortices are around, the field is not circularly symmetric, and B picks up the leading lack of circular symmetry. So it's quite an interesting measure of this property of the vortex. This formula, it's easy, from this formula it's easy to check the metric is scalar. So there are these other arguments based on the fact that the Moduli equations are a moment map condition, and therefore this modular space is a Kähler quotient. But here we have a sort of direct proof. One can easily check that this is Kähler because this sort of well.
This is really a completely exact formula.
This is exact, yeah. And it works on a general surface M, right? So Strawn originally proved this sort of rather algebraically for hyperbolic vortices, which are exactly integrable, where you can actually write down the vortices in terms of rational functions. But Samuel showed it was more general than this. Yeah, that's exact. Very nice result. So on a one vortex moduli space, the metric simplifies to this. So there's sort of this background term. So this is the term you get for a point particle. You just get omega dz dz bar. But this is a correction to the point particle picture of a vortex. In the plane, this is zero by symmetry. So you know, a vortex in a plane behaves like a point particle of fixed mass. Now, thing to note here is that they're in the same conformal class. That wasn't obvious a priori. So the metric on the moduli, the moduli space is conformally equivalent to the surface you started with. So that's a non-trivial statement for a surface of higher genus, that the metric is in the same conformal class, but it's conformally different because this isn't omega, there's a correction term. So this term is expected for a point-like vortex, and here for one vortex, just as before, B is the coefficient in this expansion. So that's just a restriction to one vortex, what I wrote before. And it measures the deviation of the vortex from circular symmetry near its center. And so one can use that fact to do a calculation. So I managed to work out what is the vortex. Suppose you have a vortex on a sphere. Well, intrinsically, the vortex is still circularly symmetric. So here's a vortex on a sphere, round sphere. But in this formalism, I have to choose some complex coordinates. So I have to do some stereographic projection. And then I have to project this field up to here. And then it turns out that the contours, one can work out explicitly in terms of these contours, and they're not circular anymore, they're elliptical. I didn't draw very well. So just by this stereographic projection, and one can work out what the B is just by elementary geometry without actually knowing what the exact solution is. And so, what happened to my
Try
projecting?
pushing the board all the way down. Maybe it detected it.
Oh, very clever. And the lights go off as well. Right, can you see this still?
Can you turn the lights off with those switches? I don't know.
Interesting to say.
I
More things.
I don't know which of these switches. It's main lighting, but it's not that, it's board lighting.
I think it's okay.
Right, so I managed to work this out using this argument, and you do find a correction to this omega. On a sphere, there is a correction to this point particle formula, but it's just a constant. Because of spherical symmetry, the metric must be just a constant times the naive metric, and it depends on the radius. So, rho, this is the standard metric on a sphere, this is a radius. And the radius can't be arbitrarily small because of this bound, this constraint on the area. Rho must be 1 or bigger. And so when rho goes to 1, the vortex dissolves. Rho can't be less than 1.
Was that the moduli space just becomes a single point when rho equals 1?
It collapses, yes. Yes, that's what we
That's
call
there's only
dissolving
one, yeah.
mortices. Yeah, metrically it's a point. Yeah, the metric becomes 0. And there's some generalizations of that, not just this round case. I worked on that with Nuno Ramal, the nature of the metric in this dissolving limit.
So just whenever the area is 4 pi exactly?
Exactly, that's right. So we studied what the metric was like when the area was 4 pi n
Plus epsilon.
plus epsilon. Yeah, we did that asymptotics as well, but I'm not going to talk about it. Right, so that was a particular calculation. Another thing we can work out is the complete volume. I should say that this B is not known in any detail because the vortex solutions are not known, even in the plane, let alone on general surfaces. So these B's are, something we can work out numerically or something, but they're not known generally. However, despite the fact that the actual metric is not known, one can work out the volume exactly. So this is assuming that the underlying surface is compact, and so n is finite. So we've got a Kähler metric, and hence a volume form, the nth power of the Kähler 2 form divided by n factorial, and we can actually work out the total volume It turns out that's all very nice. So this work I did with Nazir, and so the total volume of this moduli space just depends on integrals of the Kähler-2 form over homology 2 cycles, and can be determined exactly. So one has to just look at some particular 2 cycles, basis 2 cycles. So one 2 cycle is n coincident vortices, so that's just got sort of one complex coordinate where they all are. And another 2 cycle is if you keep n minus 1 vortices fixed, but just allow one to move, that's a 2 cycle. And we've got to integrate a 2 form over those cycles, and it's a closed form, so we can again integrate by parts, and it reduces to again this sort of integral around a singularity. So for example, for the second of these, you know, one vortex can move about, but you end up doing an integral when one vortex is very close to all the others. And so we could do that integral because we know what the B's are like when the vortices are close together. We know the limiting form of the B as 2 vortices or more vortices coalesce. So using the known pole-like behavior of these B's when vortices coincide gives us this complete closed formula for the moduli space volume. And it does depend on the area. It's not purely topological. So N, G is the genus, little n is summed over. So those are purely topological things, but the area of the underlying surface is not. But it doesn't depend on any other details of the surface, only its total area. And this formula is consistent with the idea that 4 pi n has to be less than A. And so this is the general formula, and then you can work it out for one vortex. That's when little n is 0. Sorry, it depends on the genus, but the sum stops at little n equals capital N if capital N is less than G. So if there's only one vortex, there are 2 terms. There's the n equals 0 term and the n equals 1 term. And this is the area. That's the leading term from little n equals 0, and that's the term from little n equals 1, and when you add them up you get this. So this is the area of the one vortex moduli space, and that's exact. And for example, it agrees with this this example, so that's an example that agrees with that.
So what does that mean then if you have a surface of higher genus and the area collapses to this lower limit? There's still a lot of freedom.
Oh, this goes. I mean, there's a Jacobian. Oh gosh, on the spot. The whole moduli space doesn't collapse. Part of it does, and part of it doesn't. There's a Jacobian over a complex projective space, and in the limit, the complex projective space collapses, but the Jacobian doesn't. And the Jacobian has some area which is captured by this formula, even though the other bit collapses. Yeah, that is it's interesting what happens. Yeah. Yeah, there's sort of standard result for this symmetrized nth power of which is a yeah, the thing has a Jacobian, and it's I worked in this with Ramal, but I'd rather skip it here. Right, so knowing the volume of the moduli space turned out to be very useful physically because one can work out some statistical mechanics of vortices. One can treat multi-vortex dynamics at finite temperatures, classical statistical mechanics on the moduli space. So formally, there's just one particle moving around in the moduli space randomly. That actually describes n vortices moving around on the original surface. And you have to work out a partition function, which is some integral of the cotangent bundle to this moduli space, which is the phase space in statistical mechanics. The vortices are classically indistinguishable. That's a nice feature. Classical statistical mechanics of n particles usually has a problem that you have to put in an n factorial by hand, if you know any statistical physics. Here it's automatic because the moduli space already is divided by n factorial, by the permutation group. There's some momentum integrals to do and some position integrals in phase space. The momentum integrals are Gaussian. They correspond to the kinetic energy on the moduli space. So you can do those directly. You're left with an integral which is the volume of the moduli space. You have to integrate over momentum and position. And the position integral is the integral over Mn. So that gives the volume. And there's no potential energy, it's just a kinetic energy appearing in the Hamiltonian. And then, having got the partition function, you have to differentiate with respect to the area to get the pressure. And that gives this equation of state. And it turns out this is true for vortices on any surface. The genus drops out in this formula. Statistical mechanics doesn't notice the genus, at least classically. And notice this is not the ordinary ideal gas. The ideal gas is pressure times area is number of vortices times the temperature. But here there's this correction term, which is a bit like a van der Waals equation of state. And it's due to the fact that the vortex has finite areas. It's like the equation of state for a gas of disks moving around on the map. In fact, it's an exactly solvable model of the statistical mechanics of hard disks. So if you read the statistical mechanics literature, for hard disks moving in a finite area, that's not exactly solvable because of complicated overlap integrals. This one is exactly solvable because the volume of the moduli space is exactly that. So this is not appreciated by statistical mechanics experts as an exactly solvable interacting gas, but that's what these vortices are.
When you said it was like Van, when you said it was like Van der Waals, it doesn't have a phase transition, does it?
No. So Van der Waals has two parameters in it, and this only has one. This is, I think it's called the Clausius or equation of state. So Van der Waals.
I mean, it's just excluding volume.
Yeah. So Van der Waals has two parameters in. One is due to a real force, and the other is due to an excluded volume. This has the one term but not the other, and because of that, there is no phase transition. This equation of state becomes singular at a equals 4 pi n, which is a finite area, but it's an excluded volume. It includes excluded volume effect, but not the true force, and therefore there's no liquefaction. It would be quite interesting to sort of try and extend this to include some sort of vortex attraction. Then there would be liquefaction, perhaps. I've not looked at that.
Can I ask a question?
Yes.
In StatMech, if you do hard spheres or hard disks, there's a weird factor of a half that appears in that excluded term, where it's not the volume or the area of each
You're right.
object, it's a half.
That works if you look in detail.
Or it does, that appears.
Yeah, that's in our paper, some remark about that factor of 2. You're right. It's to do with whether it's the radius or twice the radius and things like that. So this is a nice, exactly solvable statistical mechanics. By the way, this is not truly the equation of state for vortices, because if you go to this dissolving limit, this is the moduli space statistical mechanics, but vortices actually have sort of more degrees of freedom when the pressure gets lower. This equation says the pressure becomes infinite when A is 4 pi n. That's actually not strictly true because of further degrees of freedom that have been ignored.
But that's going out of the Bogomolny.
Yeah. High temperature excitable amounts of that.
Yeah, that's the problem with it. Yes, there's a singularity in this dissolving limit, but if you think about it, that can't happen. So unfortunately, this is exact, but it's exact for moduli space dynamics. Let me try and go through the scripture because I want to get on to monopoles. So this is one vortex on a surface with small curvature. This is some asymptotic. So we have to do some numerical work, but we have some understanding of the metric for one vortex on a surface with small curvature. So we consider one vortex on a surface. We scale the surface by a big factor L. Then the curvature is of order L to the -2. Each derivative contributes L to the -1 because I've scaled everything by a big factor, length factor L. And one could also consider small vortices on a fixed surface. That's physically equivalent. And then this metric is not known exactly, as I mentioned before, but we know it's of finite size and exponentially localized. So with Maciek and Daniele Dorigoni, we proposed the idea, this was a proposal, this isn't a theorem, that the metric has the following expansion. It's a formal asymptotic expansion in 1 over L, this length scaling. So 1 minus the Gauss. So we want to modify the point particle metric. So the leading term is just 1 times that, and then there's a curvature correction. So K So K is the Gauss curvature of the surface at the vortex location. K is at where the vortex is. And then that's a correction. Then this is the Laplacian of the Gauss curvature. This is the Laplacian of the Gauss curvature squared and so on. And this is a formal expansion in 1 over L.
So this is Laplacian with respect to the scaled metric?
Yes.
That's the point.
Well, no.
No, so-
The metric is now fixed, but it's got a large parameter in it. So this is of order 1 over L squared. That's of order 1 over L to the 4th. That's of order 1 over L to the 6th. And so is that. So this is a formal expansion of what the metric could be in terms of local quantities. So we believe these are local because the vortex is localized. It's almost point-like. And there's some of these unknown coefficients. Now, one constraint on this expansion is that the area of the moduli space is known exactly. So this expansion has to be consistent with what's known about the area. And the integral of the 1 gives the area of the underlying surface. The integral of k times omega by Gauss-Bonnet gives the genus. So we've got to get agreement with this integral formula here, this one. And you see that's why this k has to be here with coefficient -1. And then these terms are all the Laplacian, so they all integrate up to 0. And we've left out, for example, a term k squared because that would have the wrong integral. I mean, that has sort of an unknown integral. So this formula is an expansion which is consistent with knowing the exact area of the moduli space.
So, I mean, is that how you came about this expansion, or
Yes. Yeah. So these are the only local terms that we can think of. Things involving the Gauss curvature and its derivatives and its Laplacian. It's got to be scalar. It's got to be geometrically scalar quantities occurring here.
Well, the point is that these terms would also arise in the Ricci flow, but with different coefficients. I think you were guided by the Ricci flow, aren't you?
Yeah. Well, that was sort of
initially.
Yeah, that was a conjecture, but it's not exact. Yeah. So this argument doesn't determine these coefficients alpha, beta, and gamma, but we believe they're universal. So we worked them out numerically. So we took some examples where we could do things exactly, and we worked out alpha, beta, and gamma. And one thing we made use of to do that calculation is we didn't work with a metric directly, we worked with a Kähler potential. So this vortex moduli space has a Kähler potential, and that's itself a nice thing to think about. So the metric has this Kähler potential. That's the underlying Kähler potential on the original surface. And then these are correction terms consistent with this expansion with the same unknown coefficients. And we try to work out this. So fortunately, there's a general integral expression for the Kähler potential for the modular space of n vortices. Analogous expression used for the modular space of n punctured ring associations. I don't fully understand this analogy, but work of Takhtajan and Zograf. So Takhtajan's here. We'll be here.
we'll be here.
We'll be here. So, I'm very interested in this. Sorry, yeah, there you are. Sorry. So, I mean, there's some interesting analogy between these vortex equations and pure Riemann surface theory with punctures. The vortices all behave a bit like punctures on surfaces. So we got a formal similarity, but it's not the same. But we ended up with this, that the Taubes equation comes from this Liouville type action. If you vary this action, you get the Taubes equation. And this term is the Liouville action, but there's this interesting correction. That's a feature of the vortices. But again, you have to regularize it because it's got singularities, and this is a regularization term. You have to remove disks around the singularities. So this is a standard sort of way of regularizing action. And it turns out this is the Kähler potential. So you evaluate this S, and it's a function of where the vortex is, and you check the Kähler potential, because if you differentiate this with respect to the vortex position, you find it's equal to 2b. And that's exactly what you need to, going back here. Yeah, you see, what is the Kähler potential? Well, you want to write this as d2 by dz bar dz of something. So if you can write b as d by dz bar of something, you're in business with the Kähler potential. And that's exactly what this happens here. That something is S. have got a bar on here. Perhaps there should be a bar. So 2b is ds by dz bar, I think. And that's why this is a Kähler potential. There's regularized Liouville type action. And the total Kähler potential involves the Kähler potential of the original surface as well. So anyway, we could work out that Kähler potential by integrating. We could do this integral numerically for certain solutions and therefore work out these coefficients. And here they are. And we don't understand these coefficients. They don't seem to be nice numbers. And this is only part of an infinite expansion. These are just the three leading terms. Anyway, so that was to do with understanding a vortex on a surface of small curvature, big surface of small curvature. And we found there's a difference between the geodesic motion on the modular space and the geodesic motion on the original manifold. And the difference comes from the the main difference comes from this K term. So without all these other terms, we just have geodesics on the original manifold. The first correction is the K term, and when you work out the equation of motion for the geodesic, you find there's a force which goes like the gradient of K. So the Gauss curvature affects the vortex motion. And it's the gradient of the Gauss curvature is the force. Leading effect is a force on a vortex proportional to the gradient of the curvature. So nothing similar has been done for monopoles on a slightly R3 with a small curvature.
Do you mean a curved R3 but dt squared, the coefficient dt squared is just 1 or minus 1?
I think so, yeah.
Because I don't see how you can have Bogomolny equations unless that's true.
I think you can have Bogomolny equation on an arbitrary 3 manifold. Arbitrary Riemannian 3 manifold.
Yeah.
That's what I have in mind.
Right.
So
So that means you must make the dt squared coefficient 1, I think.
Yes, it doesn't satisfy Einstein equation.
I'm not worried about Einstein equations, just the Bogomolny equations.
No, it's okay with a dt squared, yeah. Your standard kinetic term, yeah.
Yeah, but I mean, that's what I'm saying. The coefficient of G naught naught has to, or GTT.
It's 1.
Has to be 1.
Yes,
For that to work.
yes, that's what I implied, yeah.
Yeah.
Only spatially curved, yeah. There's some remarks about gravity which I haven't really worked out. So there seems to be some analogy with results in gravity. Okay, I was wanting to spend the rest of the time on monopoles, so can I have a 1 minute break? So.
So if you consider more centers, do you have any results?
Sorry?
Consider not just one.
Yeah, we studied the Samuel studied the scattering. So the geodesic motion of two vortices involves the scattering. Two vortex modular spaces cone with a smooth top. Geodesic motion is curved. Flat asymptotically.
Yeah, they bring out their hearts.
I don't understand it. Good. But not the form I used to.
That seemed to make it go off.
Yeah.
Okay, shall I continue? So,
Yeah, okay.
Vortices are a very special kind of soliton. You saw that one can do various things with them. They're asymptotics. One can study one vortex. With monopoles, conceptually it's a bit similar, but one can do different things. I mean, some things one would like to do are not the same. One can't do. So what is a monopole? Well, first of all, it's a gauge theory soliton in 3 dimensions, and I'll only be talking about the background space being flat R3, because almost nothing has been done in detail to study monopoles on a curved R3, although I think that's perfectly well defined. It's in a Yang-Mills Higgs theory, but now non-abelian, SU2, and actually it could be a general gauge group, but the simplest case is SU2. And the fields are an SU2 gauge potential and adjoint Higgs field. That means Lie algebra valued Higgs field. And they combine into a field tensor F and a covariant derivative d phi. And static monopoles obey the Bogomolny-Prasad-Sommerfeld equations, BPS equations, that the magnetic field is the covariant derivative of the Higgs field. So there's a structure not like vortices. But again, this comes from minimizing an energy expression and completing the square and so on. It's also the moment map condition for the action of gauge transformations on fields. So again, there's a moduli space, which in this case will be hyperkähler. And I'm not going to show this because it's not easy to directly prove using physics argument that it's hyperkähler, but that's the mathematicians' arguments based on this quotient, hyperkähler quotient construction sort of show it. That's the best way of showing it. B physically is the spatial magnetic part of F, so it's a vector, although the field tensor is a 2 form, B is really a 1 form, and so you can identify it with this D of 5 as a 1 form. And there's a 4 n-dimensional moduli space of n monopole solutions. So I won't go through all the details of defining a Chern number and talking about the topology or proving existence of solutions, which was again done by Taubes originally. So there's a big technology of this, and these are the results that emerge. So the moduli space means solutions of this up to gauge transformations, and there's a boundary condition, which is that the magnitude of this phi has to go to 1 at infinity. That sets a length scale and a mass scale. And this condition, from a physics point of view, induces a Higgs breaking, Higgs mechanism. This SU2 gauge group is broken to U1 at infinity, which means that the long-range fields are not all the fields, but only the electromagnetic field, which is the U1 part of this, and the magnitude of phi still survives out to infinity as long-range field. It's best to write this as 1 plus another field, little phi, which tends to 0 to infinity. And both little f and little phi have long-range fall-off when you have monopoles, so Coulomb type fall-off. And actually these are the asymptotic behaviors for a single monopole. You have an abelian magnetic field is the gradient of the sort of scalar, ordinary scalar field, and the basic spherically symmetric monopole, which was found by Tuft and Polikov, and then Prasad-Sommerfeld found exactly asymptotically looks like a magnetic monopole, where the B, the magnetic field, is a Coulomb type, 1 over r squared fall off, and phi is a Coulomb kind of potential, minus 1 over r. And so this monopole has magnetic charge 1 and a scalar charge 1 in units of 4 pi. I've simplified factors of 4 pi in this whole discussion. So the fact this coefficient is 1 and the fact this coefficient is 1 means that the charge is 1, and there's a scalar charge as well. So a monopole is both a magnetic object and a scalar object at the same time. This is an abelian approximation, and this formula clearly breaks down at r equals 1. So if you put minus 1 over r here, you'd get sensible answer only down to r equals 1. But a monopole makes sense for r less than 1, radius less than 1, but you get the full non-abelian structure in the interior. And the fields in the core are smooth. These fields are singular at the origin, but that's not true for the monopole. The monopole is a smooth soliton object, and it's got a finite mass, which is also 1 in my units. Now, an important fact here is that it's magnetic charge and scalar charge, but there's another kind a modified solution called a dion. It's also quasi-static. So you change the equations, Bogomolny equations a bit, and you include a non-zero time component to the gauge potential proportional to the Higgs field with some real coefficient Q that's arbitrary, and you also modify the electric field to include, so that it's Q times the magnetic field. It turns out that this sort of ansatz, together with the Bogomolny equation, gives a consistent solution of the full Yang-Mills Higgs equations. And you now have an electric charge as well as the magnetic charge, because the electric field is Q times the magnetic field. So there's an electric charge, little q. And that's called a dion, things which are magnetically and electrically charged. And the scalar charge changes because the solution actually has a slightly different coefficient up here. The scalar charge is 1 plus q squared. So the size and scalar charge change a bit with q. Change quadratically, actually. So this is called the dion solution, the Julia Z dion. It's not strictly static because whenever you have an AT being non-zero, the fields are not really static. They're time independent, but if you do a gauge transformation to make AT equals 0, then the fields become time dependent. And so that's a way of thinking about the dion. It's really a time dependent object. Yeah, I'll say a bit more about that. Then there's some forces between these dions. Two dions with magnetic charge 1, equal electric charges, and scalar charges root 1 plus q squared exert no static force. So you can have two dions in static equilibrium, provided they have the same electric charge. And the reason is that there's three forces operating. There's a magnetic repulsion, there's an electric repulsion, and there's a scalar attraction. And the coefficients are such that 1 plus q squared minus this is 0. So two dions with equal charge can be at rest. But if the dions are in relative motion, or if they have distinct electric charges, then there will be forces, and these dions will move. And that motion, because the forces are quadratic in velocity and or electric charge, these forces can be interpreted as rising from geodesic motion on moduli space. So there's going to be a moduli space of n monopoles, or two monopoles in simpler case, and the geodesics on that moduli space will be interpreted as dion motion. And I will say more about that later. So simplest is one monopole dynamics. So it's quite interesting. It's important to think about the gauge where AT is 0, so you have to do a gauge transformation to do that. And now the dion is time dependent. The dion is approximately an internally rotating pure monopole, internally because of their various gauge components of the gauge potential, which are changing harmonically with time, sort of moving in a sort of circularly with time. And so the field is periodic. There's a definite period, which is the period increases as the electric charge gets smaller. And the field is periodic in this gauge. It's actually period up to a localized gauge transformation. So the monopole has a position. So thinking about moduli, you should think of the monopole as having a position, where the center is, and also an angle. Because this dion is periodic, if the angle increases by 2 pi, you should think of that you've come back to the same configuration. So the moduli of a monopole are its position and a phase angle, chi, which is normalized to run from 0 to 2 pi. And then the time derivatives of these moduli are related to the physical notions of velocity and electric charge. So the time derivative of the position is obviously the velocity, x dot is v, but the time derivative of chi is identified with q. And in suitable units, you can work out the energy, and it's a half v squared plus a half q squared. So it's important that the ratio of these that these have the same coefficient. And that's a calculation to show that. This is the energy of geodesic motion on a flat space. So this kinetic energy, with q interpreted as chi dot, can be interpreted as geodesic, the energy for motion on a flat moduli space after E crosses the circle. And this is moduli space is a moduli space of static monopoles, but then the moduli are time dependent. And the metric on the moduli space, read off from this, is dx dot dx plus d chi squared. So physically you have a half in kinetic energy, and you have dots, but metrically you have just dx dot dx plus d chi squared. And the monopole actually does deform when it's moving. As you'll know, if a monopole is in motion, it will be Lorentz contracted. And that's an effect at order v squared. And similarly, it's deformed at order electric charge squared by a small amount. It slightly changes its radius at order q squared. So we treat q as small, like the velocity. So there's this flat moduli space for monopoles, which is four-dimensional. It's got position and a phase. Now, for n monopoles, it's known that the moduli space 4n has dimension, moduli space mn has dimension 4n, so each monopole has a position and a phase, and it's hypercalar. And monopole dynamics is approximated by geodesic motion on the moduli space. You can separate off the center of mass velocity and the overall electric charge. They split off metrically, so that it's a metric product of a flat space with a relative moduli space. So the relative moduli space has dimension 4n minus 1, and this is an interesting curved manifold, whereas this center of mass part is flat. And for n equals 2, the relative moduli space has dimension just 4n, and that relative moduli space is the Atiyah-Hitchin manifold with the Atiyah-Hitchin metric, which is a very beautiful metric, complete Riemannian metric, which is also hypercalar, self-dual in 4 dimensions. For n greater than 2, this relative moduli space is not really known in detail, although perhaps some people here know more about it than I do. So how do you understand some aspects of this moduli space? Well, formally, it's defined physically using the kinetic energy of the field theory. So this is the electric field, this is the covariant time derivative of the scalar field. So again, the electric field is basically the time derivative of the gauge potential, and this is the time derivative of the Higgs field, but with correction terms that project out the part of these time derivatives that are orthogonal to gauge orbits. So it's the same idea as for vortices to define this, and it's equivalent to the L2 norm on the gauge, on the quotient space of the field theory by gauge transformation. So when monopoles are close together, it's not so obvious what the moduli are. So remember from vortices, the moduli were the locations of the vortices, these points capital Z, K. But for monopoles, there's no such precise characterization of what the moduli are physically. They're roughly the monopole positions, but it's not well defined. However, well-separated monopoles have a definite position and phase. Monopoles are a finite size, so you've got a monopole here, it's got a position and it's got a phase, which gives it an electric charge, and there's another monopole here, and so you can now treat the moduli as positions and phases when they're well separated. And there are various ways of understanding these positions and phases, for example, in terms of rational maps and their poles and residues. Dynamically, these monopoles have a velocity and an electric charge, and when there's more than one monopole, the velocity can change through long-range interactions. But here's an important point. The electric charge of a monopole is conserved unless the monopoles get close. So asymptotically, there's no interaction that changes the electric charge of a monopole. Even though the monopole can be deflected in its spatial trajectory, its electric charge will be conserved. And this is sort of clear in terms of an asymptotic symmetry of the Atiyah-Hitchin metric if you've got two monopoles. And the reason charge is conserved is because this is electric charge. Electric charge exchange is due to the short-range massive gauge fields of the non-abelian theory, which are called the W bosons. And they are massive, so they are classically exponentially suppressed. So there's electric charge is conserved up to exponentially small corrections, whereas velocity is not conserved. There will be forces on monopoles, they will scatter, and the forces will be algebraically small in the separation, not exponentially small. They'll just be 1 over distance squared or something, forces. And so I studied first for 2 monopoles, and then with Gary, we studied in detail what this moduli space metric would be for n well-separated monopoles. And we knew the moduli were positions and a phase for each monopole. And we effectively found the equations of motion, treating the monopoles as point particles. And the point particles have charges. They have a magnetic charge, they have an electric charge, which is related to this time derivative of a phase, and they have a scalar charge, as I explained for one monopole. So we could work out from physical ideas of electromagnetic point particles and scalar point particles what the equations of motion should be. And then it turns out one can cast those equations of motion in the form of a geodesic dynamics on a moduli, on an asymptotic moduli space. So the variables we worked with are the position and the velocity of the monopole and the electric charge. And the electric charge is a constant. So we basically get equations not in a 4-dimensional moduli, 4n-dimensional moduli space, but a 3n-dimensional position space. But we want to recast it in a 4n-dimensional language. And we did that by treating Q as a Noether conserved momentum for a phase chi. This is the Kaluza-Klein idea that electric charge can arise from motion in a hidden circle. So we could use that explicitly to turn our parameter Q into a dynamical angular momentum on a circle. So the asymptotic n-monopole metric, in fact, has an nth power of the circle as a symmetry, so by construction. So in practice, we didn't actually find equations of motion. It was easier to find a Lagrangian because we do Lagrangian dynamics for these monopoles, and they're dions because they also have electric charge. And the electric charge in one monopole interacts with the gauge potential of another. You see, when you have a monopole, it produces some magnetic field, and it has a Dirac kind of potential approximately to describe the magnetic field. And then how does a charged particle interact with that? Well, there's a standard electromagnetic Lagrangian for a point electrically charged particle interacting with a background magnetic field. So we use the standard formula. You need the vector potential for that, which is this Dirac potential, and the interaction term in the Lagrangian is the electric charge, the velocity of the particle, dotted into this background Dirac potential. But there's some novel effects here because we also have magnetic charge interacting with the electric field of the other monopole. And that has a similar interaction, so I won't write it down.
Excuse me, before you go on. So this S1 to the N symmetry, is that, to say this exactly, do all those S1s have the same size no matter where you are asymptotically?
No, they're a bit variable.
Yeah.
They have a well-defined limit at infinity, which is a fixed.
That's what I mean. So as you move around infinity, the
At
S1
infinity, they have a fixed size, but I'm interested in the subleading effects.
Yeah.
It's the fact they vary with separation.
That's what I'm saying. So as the separations of the monopoles vary, then the S1s vary in size?
Correct.
Yeah.
Correct. Although when S goes to infinity, they go to a fixed non-zero size.
And you fix the distance between the particles and graph infinity, you get the same.
I guess suppose you go off.
If you're far from diagonal and go to
So I'll show you
infinity, then get the same
later,
answer, but-
roughly the radius goes like 1 minus 1 over S. So this is for 2 monopoles separated by, with separation S, the radius of that circle is 1 minus 1 over S.
But suppose you have 3 monopoles and they're going off you know, separating conically.
To sum of terms, yeah. Sorry.
Yeah, so you have 3 monopoles that are going off asymptotically, right?
Yeah.
And you have circles for you know,
Yeah.
each one. Do the sizes of those circles asymptotically as you've gone to infinity, do they depend on sort of the angles of separation between these guys?
There's a formula for that. It's in
But they do vary, yeah.
They do vary, but
Yeah, yeah.
but they tend to a
It's a sum of
constant
terms, right?
as the distance
No, no,
goes
no.
to infinity. Yeah, this. I mean, if there are 3 monopoles, this gets corrected to something like. Well, I forgot.
Now, I understand at finite distance, there's definitely correction terms,
Yes.
you know, and I guess I'm trying to say just, you know, as you've gone off to infinity,
Yeah.
there are different points in, you know, of this magnification where you have different angles between the monopoles as
Yes.
you've gone off.
Yes.
The sizes of the circles depend on those angular
No.
variables? They don't?
No, they tend to 1 at infinity.
Okay,
Yeah.
gotcha.
There are sub-leading effects.
No, I understand.
But,
And there's always a center of mass circle which really is constant.
oh, that's right. Yeah. So for 3 monopoles, the center of mass
Yeah, no,
splits
yeah,
off,
yeah.
and that has constant radius, independent of the separations. But the relative moduli space, you know, has non-trivial. The radius depends non-trivially on the separation, and that's part of what contributes to the dynamics.
Gotcha.
And this constant center of mass circle is kind of obvious from the hypercator property, but from this elementary viewpoint, it's a surprise. Isn't it?
Yeah. So from our calculation, we explicitly split it off,
Yeah.
but it wasn't quite obvious. Yeah. That's right. Yeah. Right. So I'm trying to show you the ingredients of how you work out these dion interactions. So each dion has a scalar charge, a magnetic charge, and an electric charge. So when they're moving, the magnetic charge of one interacts with the electric charge of another. The electric charge of one interacts with the magnetic charge of another through these kinds of terms. But there's also the interaction of 2 magnetic charges. So the leading thing is just the Coulomb force. But that's going to cancel against the scalar force because the static forces are 0. So we have to work to higher order. We have to work to order v squared. So when 2 particles are in relative motion, if they're both magnetically charged, they're actually electric interactions. They're sort of current interactions, which are of order velocity squared. But it's exactly those that we need. So we have to do a rather careful calculation of the interaction of 2 magnetic charges when they're in relative motion to work out the effective Lagrangian. It's sort of standard electrodynamics calculation. There's also an interaction of the electric charge with the electric charge. That's a Coulomb type. That's approximately static, the order we need. That's a Coulomb type interaction of 2 electric charges. And finally, there's the scalar interaction, and that's quite interesting. I'll make some remarks about that. So this is how you go about trying to work out the interaction of 2 scalar charges. So a moving monopole can be regarded as a source for a scalar field, 1 plus phi, where phi is approximately minus 1 over r. Now, how does a second monopole interact with that one? Well, you start with sort of the notion of a Lorentz invariant action for a particle moving in a scalar field. And that's, so S is an action, and it's this integral along the world line. This is kind of relativistic notation. Ultimately, we're interested in non-relativistic effects, but it's best to start with this sort of relativistic point of view. So d tau is a world interval. This is an integral along a world line. D tau is the interval along the world line. And this modifies the scalar field. This actually is multiplied by the rest mass, the constant rest mass, but in my units that's 1. So this is the integral for how a monopole interacts with a background scalar field. So, you know, here's space-time now, t and x. And I'm considering one monopole moving, and there's another one here producing a scalar field. And this one interacts with the scalar field produced by the other. And you have to work out that, and you start with sort of this relativistic formula, but you convert it to non-relativistic language, so d tau becomes 1 plus half v squared dt, and this capital phi is 1 plus little phi, and little phi is, you know, it's approximately this, although there's a correction due to the motion. And yeah, so I'm interested in working at order v squared. So this is an important term. Phi times v squared is an important term. So I expand this out. I drop the 1 term. That's just a constant, the monopole rest mass. But all the other 3 terms, when you multiply this out, matter. So there's sort of a kinetic energy, which is half v squared times 1, there's the phi times 1, that's this minus 1 over r, that's here. And there's the the term you get from this times this, which is this. Now actually that scalar Coulomb interaction cancels against the magnetic static interaction. So this drops out, but you're left with this. And these are the important things. It's sort of a modified kinetic energy. This is related to your question, by the way, about the circle. This term affects the velocity squared. And there's similar effects on chi dot squared. Right, so one gets R-dependent kinetic terms, like this one. R is the separation. And a scalar potential, that cancels. The scalar strength of both monopoles can also be adjusted, take cancel the electric charge. In this formula, I assume that the monopoles had a unit scalar charge, but actually they don't. They're Q squared terms contributing to the scalar charges. So there are further terms, actually, which are like this, contributing. And then you start adding them all up, and you get this. This is the total Lagrangian for one pair of dions. So there are two velocities, velocity 1 and velocity the other. There are two charges, the charge of one and the charge of the other. And the total Lagrangian is this. It's all quadratic in velocity, because this is explicitly quadratic in velocity. This is linear in velocity, but it's linear in the charge, and that turns into a velocity of an angle. And this is the Q squared order. And you see here that there are 1 over r sort of terms multiplying this. And that's kind of the answer to your question. R is the separation of the pair. So the velocities are V and V prime, the electric charges are Q and Q prime. R is the spatial separation of the two dions. And this A is the Dirac monopole potential as a function of x prime minus x. It's not quite gauge invariant, but that's not surprising. I mean, the action is gauge invariant, even though the Lagrangian isn't. Well, I've said most of this. So it's kind of quadratic expression, and therefore it can be converted into a moduli space metric. So you have to use this Kaluza-Klein idea to replace these constants by time derivatives of phases, and when you're done, you get a metric like this. So you get some function of r times dx dot dx, which came from velocity dot velocity, and you get this coupling of the phase to the Dirac potential. So this is really time derivative language. This is a q and this is a v. And u is 1 minus 1 over r because of basically that is u there. And then there's a u inverse in this term. And okay, so that was a physical calculation of two dion interactions using a point particle method, and it gives a Taub-Nut metric. So because u_r is 1 minus a constant over r, this is Taub-Nut metric in 4 dimensions. This is the relative moduli space, and it's Taub-Nut because gradient of that u is the same as A, as curl of A. So that's the condition for this to be a Taub-Nut metric. And it's the asymptotic form of the Atiyah-Hitchin metric. So Atiyah-Hitchin had a completely different method of working out this metric, and you can take the asymptotic form of it, there's something I did with Gary, and read off that it looks like this. So we then re-derived this using this physical point of view.
So we're not bothered by being minus 1 over r instead of plus 1 over r?
Right, so that's the next point. The metric is not true Taub-Nut because of the negative sign of the 1 over r term. And this metric is actually singular at r equals 1, but the Atiyah-Hitchin takes over in the region r equals 1 and less, and smoothly smooths this out. So it's quite a surprise that the asymptotic metric is Taub-Nut-like, but not truly Taub-Nut. So there are some more complicated monopole problems where you get exactly a smooth Taub-Nut manifold involving SU3 monopoles and some special cases. But anyway, this is the asymptotic form of Atiyah-Hitchin. It's Taub-Nut-like, but with the wrong sign. But like for true Taub-Nut, you can study the geodesic motion, and remarkably, it's got the obvious conserved quantities, which is electric charge, that was kind of built in, and it's got a conserved angular momentum because of rotational symmetry, but curiously, it's got a conserved Runge-Lenz vector. And so it's a kind of Coulomb type problem with a Runge-Lenz vector, and the orbits are closed. The orbits are interesting ellipses and hyperbole. So the generic central force problem would give a spiraling kind of motion, and in fact monopole motions without the scalar charges tend to be spiraling on cones. But this gives closed orbits, which is very special for these Bogomolny monopoles. And well, I sort of presented this for 2 monopoles, but actually Gary and I did all this calculation for n monopoles, well separated. I mean, that's your question about 3 monopoles. So we've got the asymptotic form of this n monopole metric for any n, and it's not quite simple as this, but it's sort of a sum of terms of this sort. And so some conclusions. So solitons behave like particles and interact as point-like objects having various charges when well separated. The monopoles have magnetic, electric, and scalar charges. Actually, you can also study well-separated vortices. I did that with Spate, Martin Spate. Well-separated vortices also behave like point-like objects, and they interact via their scalar charges again, and they also have a magnetic dipole, which is kind of to do with the fact the vortex has a current loop. So again, there are 2 kinds of interaction between well-separated vortices, and one can work out the moduli space metric asymptotically for n vortices, which I did with Spate. The interaction of solitons with long-range non-abelian charges is challenging. So I've shown you this calculation for U1 monopoles with asymptotic U1 fields, but some monopoles have asymptotic non-abelian fields. It's very difficult to understand them physically. Eric Weinberg's worked on this. You have cloud, non-abelian cloud. So the notion of chromodions, which are sort of non-abelian dions, is a challenging subject. But that's still worth thinking about, because it's related to sort of true particle physics, where quarks have color charges. So these monopoles can have color charges as well as magnetic charges, and the interactions of those will be interesting. You know, I could study confinement and things like that. There's always a dream that by studying monopoles you get some insight into quantum chromodynamics, but it sort of hasn't really happened. That dream hasn't been fulfilled. So there's work to be done still. I've shown you that for vortex, one soliton motion is affected by the local curvature of the background. One could do this in more relativistic language with space-time curvature and gravitational effects. There's a little bit on this. I think Sutcliffe studied monopole dynamics in anti-de Sitter space, so that's a background space-time. Where the space doesn't just separate off from a trivial time coordinate. Ongoing is now work on clusters of several monopoles, which Roger Bielewski pioneered, but Michael Singer will talk about this afternoon. Tomorrow afternoon. So that's a generalization of understanding these single dions well separated. You can study clusters of monopoles when they're well separated. They're more complicated objects. I've talked about purely these solitons with exact moduli spaces and relate to this gauge theory, hyperkähler quotients and so on, and moment maps. But soliton dynamics goes beyond these kinds of solitons. There are solitons like skyrmions, which don't satisfy Bogomolny equation, and yet they behave in similar ways. They come in from infinity, they scatter, and so on. And so some of the soliton dynamics is interesting, even away from the critical coupling that we like to talk about, perhaps here. Okay, I'll stop there. Thank you.
Thank you.
Are there any questions?
Nick, back on your vortices part, you told us that you understand these B terms when the vortices are close together. Now, for your metric to be positive definite, you have this derivative. What dBs Z. What does that actually say?
Oh, I hadn't thought about that. Yeah, you're right. There's some inequalities on that, which I never thought about. By the way, more generally, I would like to understand sort of what mathematically these B's are. They are, from my perspective, coefficients in a Taylor expansion, except it's a Taylor expansion of something with a logarithmic singularity. That means they're quite interesting objects mathematically. For example, one can write down the natural thing, which is, so that each vortex has one of these B's, and it's a complex number. And the natural combination is B, R, D, Z. Now, this is not strictly a one form, because if you do a coordinate transformation of, this is sort of general stuff. If you take a function, if you Taylor expand something which has a logarithmic singularity, the coefficients of the linear terms don't transform tensorially under coordinate transformations. There's an inhomogeneous correction, so that if you think about this and do a coordinate transformation, which you're perfectly entitled to do, omega transforms as more like a connection of some sort with an inhomogeneous term. This was vital for our calculation of the volume of the moduli space. We made use of the fact that this omega was some kind of connection, but we never understood exactly what it was a connection of, or which bundle it's a connection of. I talked about this Martin spate, we never got anywhere. We now know B has another interpretation. It's this derivative of a regularized action with respect to some singularities, fixed points on which the action depends. Well, again, that action is not a scalar function because it's got to be regularized. I mean, maybe you know the answer to this. But we don't understand how to interpret mathematically these B's, and it would be really nice to do so. Are they accessory parameters in some sense? I don't know.
Excuse me.
Hello?
So is there any chance that you could interpret them explicitly when you're right on the sphere? I mean, that's and they have something to do with the conformal action on the sphere.
I'm sorry, right on?
On the sphere. So if you're looking on the, so in a general curved surface, there are going to be some.
Well, one can study n vortices on a round sphere.
Exactly. And so the question is, should you be able to sort of interpret them exactly? And
I don't think that simplifies the problem. I mean, n vortices on a round sphere is just as insolvable.
No, but I mean, I'm just trying to
Again,
find an exact interpretation from what the B's are, because you have a lot of group theory going around. So, and there.
Well, maybe.
I mean, there's an analogous problem where something like that plays out. I can describe to you later, but.
Well, it's fine to look at special cases, but my feeling is the problem is best defined on a generic Riemann surface.
I understand that, but all I'm saying is that in terms of finding the what these things mean. So the problem I have, and by analogy, is something I did some years ago, where you have the Yamabe problem on the sphere with point singularities. And so you see the subleading term is very crucial then with how you position the points, and there's balancing formulas, and they enter into all these formulas.
Yeah.
And those, if you just look at the case where you have two singularities on the sphere, then you know exactly what these B's mean. And then in general, there's going to be, for a general metric, when you have more than 2 points, it becomes complicated.
Right.
But that special case guides you with what they really mean.
So part of the problem with this vortex business is that the background metric is arbitrary, and the B's depend on that. It would be nice if the background metric itself, when something's fixed. So you've suggested one way of doing it, symmetry. Let's work on the round sphere. A simpler case still, which is very important for vortices, is the background being the hyperbolic plane.
Yeah, sure.
So in the hyperbolic plane, the whole vortex problem is integral. I could have given a talk on hyperbolic vortices, but did. So in that case, again, that's a simpler case, and I would suggest that's the better case
that's
to look
fine.
at.
Yeah, sure.
So if I want to simplify the problem, I would study vortices on the hyperbolic plane.
What's the quadratic term in the expansion that brings up the B's? Do you have anything specific?
I'm sorry?
In the expansion, the Taylor expansion that had B's as your linear term,
Yeah.
did you have anything look like curvature as a quadratic term, or did you expand it that far?
One of the quadratic terms is determined by the partial differential, by the Taub's equation, but one isn't, and I don't know anything about it. I can't remember having worked it out even numerically. Oh, I didn't write down the quadratic terms, but let me show you the linear term. Yes, so you know, there are superficially two linear terms, but this is the complex conjugate of that, because phi mod phi squared is real. Now the quadratic terms, there are, you know, there's a c times z minus zr squared, so that's a cr. Then there's, by reality, there's a c bar and there's a d z minus zr, z bar minus zr bar. This coefficient is determined by the Taub's equation. You know, it's a nonlinear equation. If you formally expand out, you find this is determined. It's something like a quarter omega at capital ZR. But this is free, and I don't know anything about it, or what it means. So this is not locally determined by the equation. Of course, it's determined globally by all vortices, but I don't know what it means. Do you think it has some meaning?